All right, so we're given two problems on 3-point crosses. Our first one, we're given this set of data, and we're told all of the dominant genes here in the paragraph that we're given, and we're given all of the numbers of the progeny. So first we need to determine the order of the genes. So our parentals are going to be in the highest frequency. So here's a parent right here, and here's a parent right here. And we can look at our double crossovers to determine the order of the genes. Our double crossovers are going to be in the least frequency. So we have one here and one here. Now, whenever we compare these two, we know that the double crossover switches the middle gene. So this N needs to be here, and same with here. So our gene order needs to be CH, CN, and then B. So to calculate this, I reorder the data in order from, I do the gene order and then the order from the most frequent to the least frequent. Because I know my most frequent ones are going to be my parents, and then my least frequent ones are going to be double crossovers, and then the rest are just our single crossovers. And it's just easier to calculate the map distances whenever it's ordered this way for me. So we can calculate the map distances. Like if we wanted, all we do is really calculate the recombination frequency, and then if we multiply that by 100, that gives us our map distance in centimorgans. So on the bottom here, we need to have our total number of progeny. And then it just depends on what we're calculating. So this one, I'm calculating the distance between H and N. So I go up here and I find the ones that are recombined. So these two are both recessive. So that's not recombined. This is not recombined. This is not recombined. This is not recombined. But all recombined because you have one recessive. We have one recessive allele and one dominant. One recessive, one dominant. Recessive and dominant, and recessive and dominant. So all of these are recombined ones. All we do is we add those up over the total number, and we get 90 over 1800, which is about 0.05 or 5 centimorgans. And so we do the same for the distance between N and B. So we're just looking at these two here. And recombined, not recombined, 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 not recombined, and then these two down here are recombined. So we add all those up, 216 over 1800, that gives us 12 centimorgans. We do the same thing for H and B. Now, a trick that I've kind of taught myself for these is if we find the order first, so we know these two are next to each other, but we just don't know how close they are. We know that the double crossovers are going to be in that number because they're right next to each other, and if they're double crossovers, it switches the middle one, and the N is our middle. Crossovers are going to be in this figure. Now, some of our single crossovers are going to be in there, but just not all of them. We can use the same trick for N and B. Our double crossovers have to be a part of those, right? And then for the two outer genes, the figure is pretty much going to be everything but the parents and the double crossovers. So all the single crossovers are going to be. So we calculate all that, and we find that we have 5 centimorgans between H and N, 12 between N and B, and then 16 between H and B. So now we need to calculate our coefficient of confidence and our interference. Here's our map here, and all we do to calculate our coefficients of confidence is we find the observed number of double crossovers and put it over the expected number of double crossovers. So we observed 9, like we found earlier. 5 plus 4 is 9. And then to get our expected number of double crossovers, we just take these recombination frequencies and then multiply them by each other, and then multiply them by our total number of progeny. That's our expected amount of double crossovers. Whenever we calculate that, we come up with a coefficient of confidence, or coincidence, sorry, of 0.83. And to find our interference, all we have to do is do 1 minus the coefficients of coincidence, and that gives us 0.17, so 17% interference for this data set. So problem number 2 here, we are given the data, total number of 1,006. Just finding the gene order is very simple. Figure out who your parents are, which they're going to occur in the most frequent. So these top 2 right here. Find your double crossovers, which would be this guy right here and this one right here. And we know double crossovers effectively switch the middle gene. So we know the order must be B, A, C from these figures. So here I am again reordering the data and organizing it through gene order and from highest frequency to lowest frequency. I just do that because I know my parents are at the top and my double crossovers are at the bottom. And again, we can find the map distances just by calculating the recombination factors for each gene and then multiplying by 100. So we have the distance between B and A. They're right next to each other. So pretty much that's going to be the double crossovers and half of the single crossovers, which are these 2 right here. We come up with 0.11 or 11 centimorgans. And we do the same thing for A and C. They're right next to each other, so we know double crossovers are going to be in this figure, and then the other half of the single crossovers, but not the parents because those aren't recombined at all. And then for B and C, that's just going to be all of our single crossovers, which is this chunk right here, these 4. Add those up. So we find that we have 11 centimorgans between B and A, 22 centimorgans between A and C, and 28 centimorgans between B and C. And just to find the map, we just take our puzzle pieces here. We know B and C are our outer ones, just like we found earlier with the gene order, which makes sense as to why they're the furthest apart. And we just calculated our centimorgans. So between A and C, we have 22 centimorgans, and B and A, we have 11. So this would be our genetic map right here.